In the previous video, we analyzed the motion of a ski jumper as she flew through the air as a projectile. In this video, we will talk about her landing. In the previous video, we answered these first two questions: how high she gets in the air at the peak of her motion and how long she is in the air. In this video, we will answer the next two questions: how far horizontally from the edge of the ramp does she land, and how fast is she traveling when she hits the ground? Let's remember the overall situation here. The skier has launched herself from the ramp with a speed of 15.1 meters per second at an angle 15 degrees above the horizontal. She flies through the air, starting at a height of 1.88 meters above the ground, reaching a height of 2.66 meters, and then coming down to the ground. Initially, we can think of her velocity as having two components, a horizontal component and a vertical component. The vertical component will change. It will shrink in size and become zero at the peak of the motion, grow in size until we reach the ground. This is because of the acceleration due to gravity acting on the skier. While she is a projectile, while she is flying through the air, if we neglect air resistance, the only important force acting on her is gravity. And so this is the only acceleration that she has. Notice the acceleration has a negative sign because we have decided to call upward positive. That is the initial direction of her vertical motion, so we're calling that positive. Now, the x component of that velocity does not change. There is no net force in the horizontal direction. There are no forces at all in the horizontal direction. And so the acceleration in the x direction is zero. And so this component will stay the same all throughout the trip. Now we are asked to find first the horizontal distance traveled by the skier from the ramp, and then we're asked to find this final velocity when she hits the ground. We found last time that the total time in the air is 1.14 seconds. Now, in the previous video, we first looked at the trip up, and then we looked at the trip down. We treated those separately. But in this case, we're going to deal with the total trip. And since we want to find the horizontal distance traveled, let's focus first on the horizontal motion. Right, these variables for the horizontal motion. We start with an initial x position of 0, in other words, here at the base of the ramp. And then our final x position right here will be at the range r, which is what we want. We calculated the x component of the initial velocity to be 14.5 meters per second. Remember, that is going to stay the same all the way through the trip. So the initial x velocity is the same as the final x velocity, and that x acceleration is 0, and that total time in the air is 1.14 seconds. So remember, in projectile motion, we must keep the horizontal and vertical motion separate. And in this particular situation, we are going to only focus on the motion in the horizontal direction. We want to find the final x position. That's what we need. And so we will try the second kinematics equation. Notice that this is specifically the second kinematics equation for the x motion, the horizontal motion, and we signify that by using all these subscripts. And looking over at the data here, the equation really simplifies. The initial x position is 0, and the acceleration in the x direction is 0. And so our range is simply the initial velocity in the x direction multiplied by the total time in the air. So that's 14.5 times 1.14, and that gives us a range of 16.5 meters. So the ski jumper travels a total of 16.5 meters from the base of the ramp. Now finally, we are asked about this final velocity, the velocity just before she hits the ground. Now that final velocity is not going to be purely horizontal, it's not going to be purely vertical, it's going to be at some angle. It's going to specifically be at some angle below the horizontal, and we can call that angle theta. And we realize then that this final velocity is going to have two components, an x component and a y component. If we can find those two components, we know that the final velocity squared is equal to the x component squared plus the y component squared, the Pythagorean theorem. So if we can find these two components of the final velocity, we can then find the final velocity. The final x velocity is very simple because it has not changed. The horizontal velocity has not changed for the whole trip. So we immediately know what that is. So now it falls to us to find the final y velocity. Now we take a look at the vertical motion, and this time, remember, we're dealing with the whole trip. We're not going to split it up into the time up and the time down. We're going to deal with the whole trip. So remember, we start out here, 1.88 meters above the ground, and so our initial y position is going to be 1.88 meters. The final y position is going to be the ground, 0. The initial y position that we calculated at the very beginning, the vertical component of the initial velocity, is 3.91 meters per second. And the final y velocity is what we need to know. The acceleration in the y direction is negative 9.8 meters per second squared. Remember, it is negative because we're calling up positive, and that acceleration is down. So in this situation, it's going to be negative. It's not negative in every situation, but since we're calling up positive, then this is going to be negative. And once again, the total time in the air is the same. Whether you're talking about vertical motion or horizontal motion, the total time in the air is the same. Well, given all of this data, finding the final velocity in the y direction is quite straightforward. We just use the second kinematics equation, like so. Notice the use of subscripts to specify that this is about the vertical motion. With an initial y velocity of 3.91 and an acceleration of negative 9.80 times a time of 1.14. Calculate all that out, and we get a final y velocity of negative 7.26 meters per second. Notice that this final y velocity is also negative, indicating that the final velocity is downward. Right? The vertical component of the final velocity is downward, and so we get a negative number. Well, now we use the Pythagorean theorem to find that final velocity. V final x is 14.5 meters per second. Square that. The final y velocity is 7.26 meters per second squared. So we square this, add them together, take the square root, and this gives us a final velocity, final total velocity of 16.2 meters per second. And so we have found how fast she is going just before she hits the ground. But we're also asked about the direction. And now we have to find this angle theta right here. Any of the trigonometric functions can be used to find this angle theta. Let's use the tangent function. All right, so we have a final velocity of 16.2 meters per second because we have these two components here. Well, now looking at our angle here, the tangent function is opposite over hypotenuse. Now, opposite this angle theta is the final velocity in the y direction, and adjacent to this angle theta is the final velocity in the x direction. So now we can figure out what the tangent of that angle is, given our values. V naught y, the final y rather, is 7.26. Got to keep that negative sign there. Divided by the x component, which has always been 14.5, and that works out to negative 0.501. Now that is not the angle, that is the tangent of the angle, and so you must use the inverse tangent function to find the angle theta. So theta is the inverse tangent of negative 0.501, and that is going to be negative 26.6 degrees. And that negative sign simply means that this is an angle below the horizontal as we expected. So in summary, she lands a distance 16.5 meters from the ramp horizontally. And when she lands, she has a velocity of 16.2 meters per second at an angle 26.6 degrees below the horizontal.